So our topic for today is the graphs of hyperbolic functions. To understand the graphs of hyperbolic functions, first we need to understand our basic exponential curve, which looks something like this: e to the power of x. If we reflect this curve along the x and y axis, we can actually derive the other three exponential curves. So reflected along the y-axis, we can get e to the power of negative x. Along the x-axis, negative e to the power of x. And if we reflect the curve of e to the power of x along both the axes, we can get negative e to the power of negative x. The reason we need to understand the exponential curves at first is because the hyperbolic functions actually contain exponentials in them. So if we want to understand why the curves in the graphs of hyperbolic functions are shaped the way they are, we need to relate it back to how the curves of the exponential functions look like. So let's start by looking at the most basic of hyperbolic functions, the sine hyperbolic x graph. Now the formula for sine hyperbolic x is e to the power of x minus e to the power of negative x divided by 2. From this equation, we can see that the two exponentials used in this function are e to the power of x and negative e to the power of negative x. So let's draw those out first. E to the power of x, negative e to the power of negative x. From here on, if we were to substitute values of x equals to 0 and increase them, we would actually get the sine hyperbolic x graph, which looks something like this. It actually looks like it's in the middle of the two exponential curves. So we can actually conclude that the sine hyperbolic x graph is actually the midpoint of the exponential functions e to the power of x and negative e to the power of negative x. So let's move on to our next graph, which is cosine hyperbolic x. The formula for cosine hyperbolic x is e to the power of x plus e to the power of negative x divided by 2. So from this we can see that the two exponential curves we get from the function are e to the power of x and e to the power of negative x. So basically this. If we solve the limit as x approaches to infinity for this question, we actually find that we have an asymptote where the two curves meet of y equals to 1. From here on, if we were to substitute values of x equals to 0 and increase them, we actually find that the cosine hyperbolic x graph follows the curves of the exponential function. So e to the power of negative x at this point, since the asymptote is y equals to 1 and that the curve for the cosine hyperbolic x graph cannot go lower than this asymptote, we actually follow it back up the e to the power of x curve. And there you go, that's our cosine hyperbolic x graph. Our next graph is tangent hyperbolic x, and from basic trigonometry we already know that this is just sine hyperbolic x divided by cosine hyperbolic x. Since we already know the formulas for sine hyperbolic x and cosine hyperbolic x, we can actually just substitute them in e to the power of x minus e to the power of negative x divided by 2 divided by e to the power of x plus e to the power of negative x divided by 2. Cancel these off and we have our tangent hyperbolic x formula. So from here on, if we were to substitute values of x equals to 0 and increase those values, we start to see that sine hyperbolic x does not equal to, but is approximately cosine hyperbolic x. This actually tells us that tangent hyperbolic x approaches to the value of 1. If we did this step from here onwards again, except this time with negative values, we sort of get the same results of sine hyperbolic x approximately cosine hyperbolic x, but this time tangent hyperbolic x approaches to negative 1. These are actually our horizontal asymptotes. Now that we've established our asymptotes, we can begin to draw the graph. So y equals to 1 and y equals to negative 1. Since exponentials are found in both the numerator and the denominator of tangent hyperbolic x, if we were to draw out the curves as well, we actually wouldn't be able to relate them to the graph because exponential is being divided by exponential. But no worries, we can still find the shape of the graph by substituting values of x equals to 0, 1, 2, 3 and so forth. Our graph actually looks something like this. Alright, our next graph, cosecant hyperbolic x, is actually our first reciprocal function graph. What this means is we basically just flip the numerator and the denominator around. Same story for the formula. We take the sine hyperbolic x formula and just turn it over. 2 divided by ex minus e to the power of negative x. Now for this particular graph, it's actually easier if we break up this equation into two parts. So 2 divided by ex and 2 divided by negative e negative x. From here on we can begin to draw the graph. If we were to substitute values of x equals to 0, 1, 2 and so on into each individual equation, we get two separate curves that do not intersect at any point and do not touch the axis. This is because the axis acts as asymptote, so you see it only approaches the axis but it does not touch the axis. Now time for our next reciprocal function graph, which is secant hyperbolic x. Secant hyperbolic x is basically the reciprocal function for cosine hyperbolic x. So once again we just flip the numerator and denominator to find the equation. As proven in cos hyperbolic x, if we take the limit as x approaches to infinity of cos hyperbolic x, we find that the horizontal asymptote is actually y equals to 1. And if we do the same thing for secant hyperbolic x, limit as x approaches infinity to secant hyperbolic x, we've come to the same conclusion that the horizontal asymptote is y equals to 1. With that being said, we can begin to draw our graph. What we do is first we take the exponential functions once again found in the equation, in this case e power x and e power negative x. So e power x, e power negative x, and also our horizontal asymptote y equals to 1. Now in our cosine hyperbolic x graph, we actually took the top half of the two curves that overlap, meaning this curve, to form our cosine hyperbolic x graph. The graph never fell below the asymptote of y equals to 1. For our secant hyperbolic x graph, it's actually quite simple. It's basically, if we were to substitute values of x equals to 0, 1, 2, 3 and so on, we would see that the graph actually follows the bottom of the two curves that intersect one another. So this is basically our secant hyperbolic x graph. Our sixth and final graph is our cotangent hyperbolic x graph. And like the other reciprocal functions, all we have to do is swap around the numerator and denominator. So in this case, it would be tangent hyperbolic x. And we know that cotangent is actually just cosine over sine. And since we know the equations for sine hyperbolic x and cosine hyperbolic x, we can once again just substitute them into the equation to get our formula for cotangent hyperbolic x. So like in the tangent hyperbolic x graph, if we were to substitute values of x equals to 0 and increase those values, we start to see that sine hyperbolic x approximates cosine hyperbolic x. But in tangent hyperbolic x, when we substitute values of x and increase those values, the answer we get is an increasing value. But in cotangent hyperbolic x, if we substitute values of x and increase those values, the answer we get is actually a decreasing value. This brings me to my next point, which is cotangent hyperbolic x approaches to 1. And like tangent hyperbolic x, this is our horizontal asymptote. But unlike tangent hyperbolic x, it actually approaches from the opposite side due to proven as when we substitute values of x and increase them, and we get a decreasing value. So do the same thing for x with negative values, and we come to the same conclusion. And we find out that cotangent hyperbolic x also has an asymptote of negative 1. Now we can begin to draw our graph for cotangent hyperbolic x. So we already know that we have asymptotes, horizontal asymptotes of y equals to 1 and y equals to negative 1. As proven earlier, the graph actually approaches from the opposite side of the asymptote. So all that's left to do is substitute values of x and plot those points out on the graph and join the curve to get our cotangent hyperbolic x graph. So when we substitute values, our curve, we get two separate curves that approach the asymptote and look like this. This is basically our cotangent hyperbolic x graph. So to sum up our entire video, all we really need to know is the shape of the exponential curve e to the power of x, from which we can derive the other exponential curves, and remember the formulas for sine hyperbolic x and cosine hyperbolic x, from which we can substitute into the equation of the other hyperbolic functions to derive the equations, the formulas for the other hyperbolic functions. And if unsure of how the graph looks like, we can always use the method of just substituting values of x, plotting them out on the graph and joining the curves together.